All right, how you guys doing today? We are all set to start chapter 23, which we're going to start talking about electric current, right? We're going to start talking about electricity moving from one place to another, okay? Now, electricity behaves a lot like a lot of other things in nature, right? We talked about pressure, right, in a fluid. If you have this situation here where you got some water up here and water down here, this has the higher pressure, and so it's going to push this water up until what? Well, until they both reach the same level, right? This is what makes your toilet work, by the way. It keeps water in the bowl. I know that's more information than you wanted to know. Temperature also does this. When you have a difference in temperatures, right? Like if it's hot inside and cool outside and you open a window, the hot air will move to the cool air, right? Now, I know it feels like that's not happening. It feels like cool air is coming in, but that's because it's replacing the hot air that is trying to leave. Hot always goes to cold, and as far as temperature, and it will continue to do that until equilibrium, until the temperatures in and out are the same. Well, this happens with electricity as well, right? Um, if when we talked about the battery yesterday, right? If we have a battery with a positive here and a negative here, and they're connected to a couple of capacitors, a couple of plates that as long as those two plates are equal charge, equal but opposite charge, there will be no flow of electrons. Okay, but as long as there is what we call a potential difference, because remember yesterday we talked about potential. If there is a difference in the potential of one and the potential of the other, then we will get a flow of electricity. Okay, now if we're talking about a Van de Graaff generator, right, if we were to stick a wire from the electricity that's coming off the Van de Graaff generator and run it to the ground, electricity will flow from that into the ground, but only for a short while, because eventually there will be equilibrium reached, right? So part of how we use electricity is to figure out how can we keep that flow going, right? Well, let's go back up here to uh, the water situation, okay? How could I keep this going? Well, one way to keep this going and to keep it from ever reaching equilibrium, right, is to throw an extra pipe in right here, okay, and right here we're going to put a pump, okay, and that pump will pull water this way and push it up this way, and that way the water levels will never reach equilibrium, right, because we're pulling that water out of this area before it reaches that equilibrium point. Well, electricity is the same way. We need to have a pump, all right, in order to keep the electricity flowing if that's what we want it to do. Okay, now remember that um, when we're talking about water, we're talking about the water molecules that are moving, right? Well, electric current, which is what we're going to talk about, has to do with the electrons moving, right? It's simply the flow of electric charge. Okay, so electric current is the flow of electric charge, right? Well, when we put electricity to a metal wire, the free electrons in the metal that are allowed to move make up the flow of charge. Okay, um, these are called, when we're talking about in a metal wire, the free electrons are called conducting electrons. They are passing the energy from one electron to the other. Okay, and that's because metals have those free electrons that are not locked in position. Now, protons in metals don't move because they're locked into the nucleus. Okay, and sometimes we have conducting fluids, and like in a car battery, you're going to have a fluid, and it's going to have both moving electrons and protons because there's some free protons in that fluid. Okay, now the rate at which those electrons flow, okay, we measure that in amps. Oops, let's try that again. Technically, the long term is amperes. And of course, it's named after a person, Andre Marie Ampere. Okay, he in the 1820s had a lot to do with measuring the flow of current. Okay, so if we're talking about current, we're talking about amps, right? And we use a capital A for the units on that. Okay, so the rate of electrical flow is measured in amperes. Okay, 1 ampere is a rate of flow equal to 1 coulomb per second. Okay, so that's about 6.25 billion electrons per second. Okay, so if a wire, for example, carries 5 amps, then that's 5 coulombs of charge per second. Okay. Think of amps as like you're measuring how many electrons go by a fixed point in a wire every second. Okay. I don't know if that helps or not, but that's the way I try to think of it. Okay. Now, remember that this charge, this flow only happens if there is a potential difference. And as we said, we can't have a potential difference. Well, eventually things come to equilibrium pretty quickly. And so it's helpful sometimes to have something that can push the electrons so that we continue to have a potential difference, right? So we need something to pump in. What do we normally use for that? Well, we usually use a battery, okay? Now, how do I want to put this? The pump, the way we measure how much that pump will pump is through voltage. Voltage is how hard something is pushing, right? Amps is how much flow there is, okay? Amps, you could kind of think of amps as like the size of the pipe, and the volts is the pump that's pumping things through that pipe, okay? So if you have one metal sphere, okay, that's positively charged, and another metal sphere that is negatively charged, right? We can develop a voltage between those two, right? Because they're opposite charges. There's going to be a potential difference between the spheres, okay? If we put a wire between them, what's going to happen though? This is not a good voltage source, by the way, because what's going to happen is it's going to get to equilibrium pretty quick. And then what? Might help if I spell right. Okay. It's really, and really that equilibrium in this case for electricity is almost instantaneous because electricity is moving basically at the speed of light. So these electrons that are over here are going to flow over here, and they're going to push protons over here, and it's going to come to equilibrium very, very quickly. Okay, so batteries and generators do the work to pull negative charges away from the positive ones in order to keep that electric potential happening. Okay. Okay, so let's clear this. All right, so another thing that can cause a push or a pull besides batteries and generators is sometimes chemical reactions. So like in a battery, in a car battery, that might be the disintegration of zinc or lead in hydrochloric acid, which is why they tell you not to open up a battery. Okay, and the energy that comes from that chemical reaction is stored and converted to electric potential energy. Okay, cars have alternators, and what an alternator does is it separates out the electrons. through electromagnetic induction, right? I don't know if you know what an alternator looks like, but it's got a lot of coils of copper wire around it, okay? And that's a generator that is going to cause electrons to move in a certain way away from the positives, okay? But here's the thing to keep in mind, that whatever work is done in order to separate those charges, right, in order to create that electric potential, that's how much potential, that's how much voltage that battery or generator or whatever has, right? So the voltage provides the pressure to move electrons through a circuit. So remember yesterday we talked about the fact that a 12-volt battery, okay, has 12 joules of energy per coulomb of charge, right? And that charge is found at the terminals of a battery, okay? Now, let's make sure we get something straight here. When we're talking about electricity moving through a circuit or a wire or whatever, we're talking about the current, right? If we're talking about the potential difference from one end to the other, we're talking about the electricity across a circuit, right? And that's volts. Okay. There, if you have water on one end that's under high pressure and water on the other end of a pipe that's under low pressure, the pressure doesn't move. The water does, right? Same thing here. The voltage does not move, but the amps are the things that are moving. So voltage happens across two ends, across a circuit, and amps happen through a circuit, okay? And it's only going to flow through again if you have a potential difference. All right. Now, one other component of electricity, and one of the whole reasons why we have electricity is because of a phenomenon called electrical resistance. Right? Electrical resistance. So resistance is something that impedes, slows down the flow of electrons through a wire or through a liquid or whatever. And so sometimes our current is affected by that electrical resistance. Voltage is not affected by resistance necessarily. It is, but the voltage is going to be the voltage, right? The two things that are going to change are your amps based on your resistance, okay? So, for example, if you were to push water through a smooth pipe versus pushing water through a corrugated pipe, right, the flow in the smooth pipe is going to be a lot faster than the flow in a corrugated pipe. And that's kind of the same thing with electricity. If we put things in the way to slow down the electricity, well, then the flow is going to be less, okay? Right, and obviously, let's bring the water comparison in again. A short pipe is going to have water go through it a lot faster than a long pipe, right? And that's the same with electricity, okay? The resistance of a wire will depend on two things, okay? One is the length of the wire, and number two is the thickness of the wire. Right, those two things will affect the resistance to electrical flow. Okay, so let's see, let me back up. Yeah, longer wires have more resistance than shorter wires, and thick wires have less resistance than thin wires. Okay, thick wires have less resistance than thin wires. Now, not only that, but sometimes the material itself could affect things. Like copper wire has less resistance than steel wire if they're the same size, right? So copper is a slightly better conductor than steel, which is one reason why homes have copper wiring. Okay. Now, electrical resistance also depends on temperature. Okay. If there's more or atoms bouncing around in a material, there's going to be more resistance, right? So the warmer something is, the more resistance there is. right? And the colder something is, the less resistance. So, and that should make sense based on our conversation about superconductors, right? Superconductors are things that are very, very cold because we have slowed down to almost a stop all of the extra molecules and atoms that might be moving around in a substance. We've stopped them to clear the path for electricity to flow through, quote unquote, unimpeded, right? There's no resistance, okay? So electrical resistance has to be considered when we're talking about current, okay? And so just to kind of sum this up today, current is equal to your voltage divided by your resistance. So when we used the example of a 12-volt battery having 12 joules per coulomb, that's only if there's no resistance, all right? So current and voltage could be equal, even though they're different units. We could say a 12-volt battery can produce might have 12 amps, for example, but if there's resistance, then that changes, okay? And I should add that the units for for resistance, are called ohms. That's supposed to be an O. Okay, guess what? Named after a guy by the name of Ohm. Okay, so we will talk more about that on Monday, but that's going to do it for the weekend. I'll have some problems for you to work on, and we'll discuss them on Monday. All right, thanks for joining. We'll talk to you later.